So welcome back to more MRI physics from MRInotes.com. Today's topic is MRA, or Magnetic Resonance Angiography. So in other words, how can we use MRI to visualize blood and blood vessels? Now, MRA isn't just one technique. It's a family of some very different techniques and approaches. So today what we'll do is we'll do an introduction to MRA in general, and we'll look at what are called black blood techniques. One approach in MRA is to use what are called contrast-enhanced techniques. With contrast-enhanced techniques, we inject a contrast agent. The action of the contrast agent is to cause blood in the vessels of interest to appear brighter effectively than everything else. So contrast-enhanced imaging is a type of bright blood imaging. It's not the only type of bright blood imaging, but contrast-enhanced is always bright blood. There are also non-contrast enhanced MRA techniques available. With these, we don't use or need contrast agent. So that will save us the cost of contrast agent and also eliminates any safety concerns we could have with the use of the agent. Non-contrast enhanced MRA isn't just one technique. There are many different options available to us. These can be either bright blood techniques or black blood techniques. So obviously, depending on which you use, blood will either appear hyperintense or hypointense. So here are some of the options we have available in non-contrast enhanced MRA. In black blood techniques, we have spin washout techniques, we have inversion recovery techniques, 3D fast spin echo methods. With bright blood approaches, we've got time of flight, phase contrast, steady state free precession, arterial spin labeling, and this isn't even an exhaustive list. So for the rest of this video, we'll concentrate on the black blood techniques and we'll pick up the others later. Okay, so the first one we will look at in detail is called spin washout. So it's one of these black blood techniques. It's inherent to spin echo type sequences, so it's really just a consequence of the way that spin echo works. So to visualize it, what we're going to imagine is that we've got a blood vessel and we're selecting a slice to image that's more or less perpendicular to that blood vessel. And the little circles here are representing just spins that are either in the blood and flowing or are in the selected slice and are stationary. So with a spin echo sequence, what's happening is, as per usual, we have a 90-degree pulse, we've got a 180-degree pulse, and then we receive an echo, and obviously we repeat and repeat every TR period. Okay. So in the stationary slice, if we take a spin that's not moving, it's going to be affected by both the 90-degree pulse and the 180-degree pulse. So when it's hit by the 90, we're indicated filled in yellow, and when it's hit by the 180, we're showing it bordered in orange. So you can see for a stationary spin, the slice is going to receive both the 90 and 180. It's going to be affected by both the 90 and the 180. So any stationary spins out here or here are going to contribute to the echo and will contribute to the image as per normal. But for the flowing spins, they might be affected by a 90. They might be affected by a 180. Remember, it's only within the selected slice that the radio frequency pulses are going to be affected. So the flowing spins might be affected by a 90, that might be affected by a 180-degree pulse, but they're not going to be affected by both. So that means that the flowing blood does not contribute to echo formation. So it means that the flowing blood is going to look dark or black. So there will be a void in the image in the slice where we have flowing blood. Okay, so this seems like a nice simple technique, and the idea of black blood is quite good for getting us contrast with the vessel walls. But if we look at it a little more, we can see straight away that it has some limitations. So here we were showing a slice perpendicular or nearly perpendicular to the flow. Say we had a case where the flow was actually in the plane of the slice that we are imaging. Well, in that case, the technique breaks down because you can see what happens. The flowing spins are in the selected slice, which means they are going to be affected by both the 90-degree pulse and the 180-degree pulse, which means they will contribute to signal, which means the black blood effect isn't going to happen. We also need to think about the speed of the blood flow through the slice. So remember, what we need is for the black blood effect to work is we need the blood to flow through the slice sufficiently quickly that it isn't affected by both a 90-degree pulse and a 180-degree pulse. So think about the timings here. So obviously the time between the 90-degree pulse and the echo is TE, and the time between the 90-degree pulse and the 180-degree pulse is TE over 2. So effectively, blood entering the slice has a time TE over 2 to get through the slice in order for the black blood technique to be effective. So if we have a certain slice thickness, delta Z, so that could be 2 millimeters, 4 millimeters, whatever, the speed of the blood needs to be such that it covers that distance, delta Z, in a time TE over 2 or faster, which means we have a minimum velocity that we need the blood to exceed for a given TE and a given slice thickness. So this means that slow flowing blood, or for very thick slices, then the black blood technique simply is not going to be effective. Okay, so that's the spin washout technique. So we saw it's a feature of spin echo type sequences, and it has a disadvantage in terms of slow flow and in-plane flow. So next one we're going to look at is black blood techniques which are based on inversion recovery methods. So just to take a step back from this, you will remember stir and flare. So they work by nulling, in the case of stir, nulling fat, and in the case of flare, nulling maybe CSF or liquids. So could we not apply something similar to blood? Could we get a inversion recovery technique and that would just null blood? So let's just pursue that idea in the next slide. Okay, so let's just remind ourselves how these inversion recovery IR techniques work. So again, this is very similar to stir flare that you will have seen before, but the general principle is we apply a 180-degree radiofrequency pulse that inverts the longitudinal magnetization of the tissue. And here we're going to be looking at two tissues. We'll call one the yellow tissue, the other the red tissue. And the T1 of the yellow tissue will be taken to be shorter than that of the red tissue. So when the 180-degree pulse is applied, the longitudinal magnetizations for both tissues are inverted, but the yellow tissue, having the shorter T1, recovers more quickly than the red tissue with the longer T1. So they behave like this. Now you can see that each of our two example tissues go through zero. The longitudinal magnitude goes through zero at some point, and the point at which they go through zero is called a null point, and it will depend on the tissue's T1 value. Now, the 180-degree pulse is just a prep pulse. It's not doing any imaging. We need a host sequence to do the actual imaging. So the host sequence could be, say, a fast spin echo sequence. We won't worry too much about what it is. It's the part that's doing the actual imaging. So what we do is we start our IR sequence with a 180-degree pulse, and then we delay a certain amount of time, which is called the TI time, and we choose that TI time such that it coincides with the null point of whatever tissue it is we are trying to null. And Ti, of course, comes from inverting time. Not to be confused with T1, even though they look the same when printed. So here we're showing the Ti chosen so that the whole sequence starts just as the longitudinal magnetization of the yellow tissue is going through 0. So if it's going through 0, that means there's no way that the yellow tissue can possibly contribute to the image that's formed in the host sequence. So in other words, the yellow tissue in this case will be nulled. And if we wanted to null the red tissue, we'd simply choose a longer Ti time. So by choosing the appropriate Ti, we can null out tissues with a certain T1. So could we apply this to blood to produce black blood? Yeah, well, we can, but after all of that, I have to tell you that this basic inversion recovery technique with a single 180-degree inverting pulse isn't actually used for black blood imaging. So why is that? Well, it's because this technique just doesn't null some target tissue with a particular T1, in this case blood. It would also reduce signal from tissues that have T1s in the same general range. So you can see here that with the yellow tissue, it's not null going into the whole sequence, but its longitudinal magnetization is certainly reduced. So in practice, if we use this technique to image vessels or the heart, we would get black blood, but we would also get reduced signal from vessel walls or myocardium. So we wouldn't get good contrast that we're looking for. So we need something a little bit more sophisticated. So in practice, to use inversion recovery techniques in black blood, the practical implementation uses a double inversion recovery. So in fact, it uses two 180-degree pulses, whole sequence as before. One of the 180-degree pulses will be non-selective and the other will be selective. Okay, to demonstrate how this works, we have a little animation running on a loop here. So what's being shown is this is a blood vessel. These are the walls of the vessel, and this is the lumen with the blood flowing through it. This grayed out area is a selected slice that we are imaging through the vessel. So it looks a little bit complicated, but let's stick with it and see what's happening. So this is our double inversion recovery sequence. So double means we've got two 180-degree pulses, and we have our host sequence as before. We've got one non-selective and one selective inverting pulse. So just initially, let's look at what's happening, the flowing blood. So the flowing blood experiences a 180-degree flip on the first inverting pulse there, and because the second inverting pulse is selective, in other words, it affects only the slice, that flowing blood flowing into the slice is essentially only affected by that one first 180 non-selective pulse. Okay. What we've done is we have chosen our Ti time such that, you see the way the blood is recovering here, we've chosen it such that the whole sequence is going to start just as the blood is going through, the longitudinal magnetization is going through 0, like there. Okay, the whole sequence is just starting. Okay. Now, if we look at the stationary spins, so here with the stationary spins in the wall of the vessel, we're showing them as yellow rather than red with flowing spins. So what's going to happen then? Well, it gets affected by both pulses. The longitudinal magnetization in the slice in the wall is going to get affected by both pulses. So it's because it's affected by both the non-selective slice and the selective slice. And two 180 degrees after one another essentially means nothing. So the longitudinal component of the stationary spins in the slice, in other words, the ones that are not flowing, remain unaffected, whereas the blood flowing into the slice, because of the way we've chosen the TI time, is going to be nulled. Okay, so remember we introduced the idea of this inversion recovery sequence to help solve the problem with the black blood approach, that with slow flow the black blood technique wouldn't work properly because the blood needed to pass through that slice thickness reasonably quickly. So what's the situation with the double inversion recovery sequence? Well, we do have one requirement. So we see where the blood within the slice, the blood that does get hit by both the selective and non-selective, that blood there, that needs to pass out of the selected slice sufficiently quickly that it's not there when we start the whole sequence. Otherwise, we won't be getting our dark or black blood effect from this approach. But it has a relatively long time to pass through that slice. It's got time TI, where remember with the black blood sequence we only had TE/2, and TI will be appreciably longer than TE/2. So this approach, the double inversion recovery approach, will be more tolerant to slow flow. Okay, so that's the inversion recovery approach to black blood. A limitation of the approach we just looked at, the double inversion approach, it's still not going to be any good for nulling in plane flow, no more than the first one we did, the spin washout. Also, it's essentially a 2D single slice imaging technique. Even if various techniques can be applied to get more slices, it's still essentially a 2D technique. So that brings us to the third and final one we will look at in this video, which is a 3D fast spin echo approach to black blood. Now, the black blood element of this is fairly complex, so I'm not going to overly labor it. I'll describe it quickly at the end. So really for this one, we're doing a quick review of what 3D fast spin echo is, and then we'll quickly bring in the black blood aspect of it at the very end. So let's remind ourselves just of the difference between 2D acquisitions and 3D acquisitions. So for the next while, this is general MRI. It's not specifically MRA. It's more background information. So if we are imaging a 3D volume, there are two ways we can go about it. One way is to simply collect multiple 2D slices. In that case, every slice has a frequency encode direction and an orthogonal phase encode direction. Of course, I could have just as easily shown the frequency and phase encode direction swapped around here, and every slice will have its own K-space to fill. The time that it takes to collect one slice is the time it takes to fill K-space. So that will be this basic formula. It will be the TR time it takes to fill one line in K-space, multiplied by NP, the number of pixels in the phase encoding direction, which is of course the same as the number of lines in K-space. Okay, so that's the time to fill one slice, but if we had 50 slices to collect, that doesn't mean that the scan time will be up by a factor of 50. With a 2D acquisition, the machine can be collecting an echo from one slice while it's waiting for echoes to form in another, so we don't have to scan one slice and then move to the next one and so on. So a 2D acquisition for multiple slices can be a lot quicker than simply scaling up the scan time for a single slice by the number of slices. The other approach to imaging a volume is to use a 3D acquisition. In that case, we have a frequency encode and two phase encodes. One phase encode as before, and the other phase encode in the slice direction. And instead of multiple 2D K-spaces for every slice, we now have one 3D K-space for the entire volume. 3D imaging brings some advantages. For example, there are no slice gaps. It's easy to reproject this data later to look at it from any orientation, and it's good for high-res and high SNR imaging. The problem is the scan time. The basic equation for 3D acquisition scan time is the product of the TR time with the number of pixels in both phase encode directions. And unlike the 2D acquisition, there is no escaping that. If you have 50 slices, or strictly 50 pixels in the second phase encode direction, then with the 3D acquisition, you pay directly in time for each of those slices. Okay, so what options do we have to speed things up? Well, what about fast spin echo? Let's have a quick refresher on fast spin echo. For the 2D acquisition case, first of all, again, there's nothing specifically MRA about this yet. Fast spin echo is, of course, a general MRI technique. So a quick reminder of how fast spin echo works. In a given TR period, we have 190-degree excitation pulse and multiple refocusing 180-degree pulses. Each 180-degree pulse generates an echo, so in one TR we can collect multiple echoes and fill multiple lines in K-space. In this example, we're showing an echo train length of 6. In other words, we're generating 6 echoes per TR, and this will collect a single slice 6 times as fast as a conventional spin echo. So can we translate fast spin echo to 3D scanning? Yes, but to make it practical for substantial volumes, fast spin echo has to be adapted or optimized for 3D. We are going to need long echo train lengths, and one problem we can see from the 2D case is how the echoes fade away with time, with long echo train lengths and echo spacing. This is just a result of normal T2 decay. To get over this problem in the 3D case, we apply some tricks. So instead of using repeated 180-degree refocusing pulse as we do in the 2D case, in the 3D case the flip angle is modulated over the course of the echo train. This serves to preserve the echo amplitude longer. Why this is so is a little bit complex, but the use of non-180-degree refocusing pulses introduces something called stimulated echoes, and these help add to and sustain our normal echoes. Another element of optimized 3D fast spin echo is the use of very short echo spacing. So that means we can pack in longer echo train lengths, and other tricks like parallel imaging are also used to reduce the number of K-space lines that need to be collected. Okay, so that's our run through our 3 black blood techniques that we looked at: spin washout, inversion recovery approaches, and 3D fast spin echo. So next time we'll have a look at bright blood techniques. So until then, thank you very much, and I hope you found this useful.